This is second part of the 22nd lecture of Engineering Physics 1. In the second part, I will continue discussing oscillations. I will do this by looking at specific questions and problems from the book. On slide number 7, we have question 22.1. In this question, you have a graph of x versus t for 3 different oscillations. So the graph looks like this. Please look at the slides. I'm not going to draw. I will actually try to draw them here. There are 3 lines: a blue line, an orange line, and a green line. And there are a bunch of questions that ask you to rank the curves by frequency, a spring energy at t equal to 0, which is here, kinetic energy at t equal to 0, the box's speed at t equal to 0, and the box's maximum kinetic energy. So I would like you to pause this video now, think about those questions, and then come back. Let's start with question A, the frequency. I think this is the simplest question. Frequency is basically a measure of how many cycles you get in unit time. High frequency oscillations look like this. Low frequency oscillations look like that. When I look at this picture by eye, it seems to me that the frequency of curve 1 is the greatest, followed by the frequency of curve number 3, and the curve number 2 looks the most stretched out to me, so the lowest frequency. Now let's think about part B, spring potential energy at time t equal to 0. So I hope you had time to think about this. This is a bit trickier. One thing to remember is it's probably best to write down potential energy for the spring. It's k delta x squared divided by 2. So you have more energy in your spring if you are more displaced from equilibrium. And if I look at this line that corresponds to time t equal to 0, it seems to me that the orange line is the most displaced. So I would say that potential energy of spring is the most in the orange line. And then we have lines blue and green, 1 and 2. They seem equally displaced to me. They kind of intersect each other over here. So I say curve 3 has the most spring energy, and curves 2 and 1 have equal amount of spring energy. Now let's think about kinetic energy. Actually, let's do it in the inverted order. Let's first think about velocity, box's velocity, v, box's speed. Again, this is slightly tricky, but not if you remember what velocity is. Velocity is derivative of x. So it's the slope of x versus t. You have to look at the slope of your curves on this line and decide which one has the steepest slope. Again, by eye, it seems to me that curve 1 has the steepest slope, followed by curve 2, and then you have curve 3, which has a 0 slope. So for curve 3, you have the least velocity, the least speed. Now we can go back to question C that asks, where does box have the most kinetic energy? We have to write down expression for the kinetic energy, which is mv squared over 2. So where you have most velocity, you have most kinetic energy. And the ranking then will be similar to D. Curve 1 will have the most kinetic energy, followed by curve 2, and followed by curve 3, which will have 0 kinetic energy at time t equal to 0. Now let's think about question E. question E asks you, what's the box's maximum kinetic energy? Let's think about what maximum kinetic energy is. I would write down the formula. I actually in the in first half, when we were taking some derivatives towards the end, and when we were talking about energies, we derived this expression. You can go back to it if you don't remember it. For the maximum kinetic energy, so the maximum kinetic energy was mass times maximum velocity, Vmax squared divided by 2, and maximum velocity is omega times a, so omega squared times a squared. And since omega is square root of k over m, the m will cancel out and we will get k times a squared divided by 2. If you look at this equation, you will see that the maximum kinetic energy is with the trajectory that has the maximum amplitude, which makes sense. And if you look at the graph, by eye, it looks like curve 1 has the maximum amplitude, followed by curve 3, and followed by curve 2. And as always, if something in this is unclear, feel free to join our Zoom help room, where I will be happy to clear this out for you. Okay, now let's do the first problem on slide number 8. This is problem 22.1. And in this problem, this is actually not a simple problem. They tell you that you have a piston, and this piston is moving up and down with a simple harmonic motion. It's moving up and down. There is a block on the piston, and if you think about it intuitively, it's clear that if this motion has a really high amplitude, at some point this block will find it difficult to be rested on the cylinder, so it will not be able to catch up, and the cylinder and the block will separate at some point. The block will be hanging in the air. The question is, if the period is 1 second, what's the largest amplitude that this motion could have without the block separating from the piston? I will give you a few seconds to think about this. After you do, please come back to this lecture. Okay, so I hope you had time to think about this as well. The trickiest part in this problem is to figure out when is it exactly that the block separates from the piston. So think about this from the point of view of a block. What block feels is, it feels the force of gravity, which is always there. And then it also feels a normal force coming from the piston. When this block moves up, it moves up because of the normal force. And there is never a problem moving up, okay? There will always be enough normal force to move it up. But when it moves down because of gravity, and gravity is something that you cannot change. Gravity is what it is. So if this block needs to move faster than gravity can move it, it can't. If the piston moves down faster than with the acceleration of 9.8 meters per second squared, then the block will not be able to catch up because there is no glue gluing them together, and it will hang in space behind the piston while piston moves down. So once you figure this out, then it's easy to solve this problem. Basically what we're looking for is, we're looking for the amplitude of this motion that will make acceleration of the maximum acceleration of the piston exactly equal to 9.8. If you look at the slides, the maximum acceleration for a simple harmonic motion is omega squared times a. This is maximum acceleration. And so if your period is 1 second, then your omega is 2 pi over 1 second. And then omega squared will be 2 pi squared. So you want 2 pi squared times a to be equal to 9.8, but not more. And this condition puts a limit on your amplitude, and this limit is that your amplitude cannot be more than 9.8 divided by twice pi squared in meters. So I'm not going to compute this number. This number is approximately 10 divided by 2 times 3 is 6, 6 squared 36. So this is about 1 foot or 0.3 meters. And if the piston moves by a larger amplitude than this, then on the way down, the block will separate. Part B is very similar. In part B, the only thing that changes is that you know the amplitude, which is 0.05 meters, and you have to find the frequency. So we will write W of omega squared times 0.05 square, 0.05 must be equal to, but no more than 9.8. And this omega is 2 pi divided by the actual frequency. What's wrong with my, okay. And from here, you will get condition on your frequency, that your frequency sorry, give me just 1 second. Yeah, sorry, this is, okay, yeah, I had a mistake here. So omega isn't 2 pi over frequency, it's 2 pi over period, it's 2 pi times frequency. So here you will have 2 pi squared times frequency squared. And this will give you condition for frequency, that frequency has to be equal to 9.8 divided by 0.05 times 2 pi squared at most. If you have more frequency than this, then the box will separate. The next problem, problem 22.2 on slide number 9, deals with a similar situation, except now you have this table that moves like so, to the left and to the right, undergoing a simple harmonic motion with a frequency of 2 Hertz. So twice per second. There is a block on the surface, and the coefficient of friction, static friction here, is 0.5. Now it's clear that if you shake this table with a really large amplitude, at some point this block will not be able to catch up and it will slide. The question is, what's this maximum amplitude where the sliding is just about to begin? This is in some ways similar to the previous problem, so why don't you pause for a few seconds and think about how you would solve it and then come back. Okay, so this problem is similar, except now the force that's driving the motion of the block is the friction force between the block and the table. If this table shakes with the frequency of 2 Hertz and with some amplitude that we don't know, then the maximum acceleration that it undergoes is omega squared times A maximum And this is 2 pi squared times frequency squared times amplitude maximum. Since frequency is 2 hertz, this is approximately 36 times 4. And what's 36 times 4? 36 times 4 is 4 to 144, about 150 times maximum amplitude. Now, what we want is we want to have enough friction here to support this kind of acceleration. So the force of friction is equal to mass times acceleration, of course, but it's also equal to normal force times mu, which is mg times mu. So from here, mass will cancel out, and you will get the following acceleration. You will get the acceleration, the maximum acceleration that this friction can support is g times mu, which is approximately 5 meters per second squared. And then for the amplitude, you will get that 150 times the amplitude must be equal to 5, but no more than 5, which will give you the amplitude, which is no more than the 5 divided by 150. This is 1 divided by 30, which is 0.1 divided by 3, which is approximately 0.03 meters. So if you shake this table with a larger amplitude than this, then the block will start sliding. Now let's move to problem 22.3, which is on slide number 10. In this problem, you have a spring that hangs from the ceiling, and there is a small object attached to it. So you hold this object at the equilibrium, and then you suddenly let it go. It's, of course, oscillating after you let it go, and they tell you that the lowest position it goes to is 10 centimeters below the equilibrium. There are 3 questions. You have to find the frequency of the oscillations. You have to find its speed when it's 8 centimeters below, somewhere over here. And then there is a third question, which is slightly more involved. In this third question, they tell you that if you attach extra 0.3 kilos to the object, then the frequency is half of its original frequency. And you have to find the mass of this object based on that information. Again, why don't you pause this video, try to solve this. If you solve it, that's great. This is quite a complicated problem. If you cannot solve it, then come back to the video and we will try to do it together. I will start by thinking about this problem. I'm thinking about what I know. So I know I don't know the mass of this object. I don't know stiffness of the spring either. All I know is that when it was released from this point, it went down to 0.1 meters below the equilibrium. I will try to find out some stuff by writing down conservation of energy between here, this 0.1, and here, this 0.2. What I will do is I will take this as my 0 level. And if this is my 0 level, then I have 0 potential energy. This object isn't moving yet, so I have 0 kinetic energy. And the spring is unstretched, so I have 0 spring energy. So my energy here is 0. At this point, at point 2, I'm not moving because this is the point of where my object stops and returns. So I have no kinetic energy, but I have some negative potential energy, which is mg times 0.1. And I also have some spring energy, which is k times del x squared, which is 0.1 squared, divided by 2. So this is my conservation of energy. Let me rewrite it. I have two things that I don't know here. It's the mass and K. So m times 10 times 0.1 is 1. And 0.1 squared is 0.01. Half of that is 0.005. M is equal to 0.005 times K. And even though I don't know M and K, it looks like I can know the ratio of K to M will be 1 over 0.005. This is 1,000 over 5, which is 200. So the ratio of K to M is 200. Now, why is this ratio important? This ratio is important because, as you should, if you don't remember, you can look it up. We derived that the frequency of oscillation, when you have this sort of a spring, mass attached to a spring, is the square root of K over M. So the frequency is omega is square root of K over M, and the frequency is omega divided by 2 pi. So I will have 1 divided over 2 pi, square root of K over M, which is 1 divided over 2 pi, times square root of 200. And I'm not going to compute this number now, but this is how I find my frequency. So I found my frequency without knowing either K or M, but I was able to find the ratio by looking at how far this object dropped when I let it go. That takes care of part A. The frequency is now found. Let's think about part B, where you have to find the velocity over here. To find velocity over here, 8 centimeters below the equilibrium, I will again use my conservation of energy. So let me erase all of this and write the conservation of energy again. This time I have 0 as usual because I started from 0 energy. But instead of mg times 0.1, I have mg times 0.08 because I'm now 8 centimeters below. 8 centimeters below, sorry. I have some energy in my spring, which is K times 0.08 squared divided by 2. And I also have some kinetic energy because my object is still moving when it's here, and that's mv squared over 2. So what I want to find from here is I want to find velocity. Let me solve this for velocity. From this equation, velocity is equal to a square root of g times 0.08 times 2 minus k over m 0.08 squared. G is 10. I may as well write 10 in here. And I have this k over m, which I don't know, but in the previous part, in part A, we figured out how to find it. So this k over m, even though I don't know k and I don't know m, this ratio I can find. I don't remember now what the ratio was. I think it was 0.005. So I will plug it in here, and this will give me the velocity. So that's the velocity. Now part C, which is slightly different, where they ask us, they tell us that when they added 0.3 kilos, the frequency halved. And they ask us what was the original mass before they added 0.3 kilos. To solve that third part, what you have to do is you have to find the frequency when you had this mass m, which is an unknown mass, and then you have to find the frequency when your mass increased by 0.3. So this is the new frequency, and this is the old frequency, and they tell us the new frequency is half of the old frequency. So half of the old frequency is the new frequency, and this is the equation. Let me solve this equation up here. I will square both sides. I will get 1/4 of k over m is equal to k over m plus 0.3. The k will cancel out, and then the only unknown is m. I can write this equation as m plus 0.3 is equal to 4m. 3m is equal to 0.3, m is equal to 0.1. Well, what do you know? Turns out the original mass that was hanging on the spring was equal to 0.1 kilos. And that solves the part C of our problem. Now, to be perfectly honest with you, these problems were kind of a bit more complicated than the ones that you may have on your homework. And I'm not going to ask you to solve problems of this complexity on the exam. And then you may be thinking, what's the point of solving this if it's not on the test? I think there is still point in this. I've read somewhere recently that it's kind of good to have lots of books in your house, even if you will never read all of them, because just having those books on the shelves in itself is inspirational. It shows you, tells you that there is a lot of information out there, and in some weird way it may motivate you. And I think it may be true, and I think it also may be true for physics and for the problem solving. Sometimes it may be motivating to see how more complicated problems are solved. It may motivate you to become better at physics, eventually, even if now you feel uncomfortable with problems of this complexity, eventually, if you are professional engineers, at some point, this should become very simple to you. This was the end of the second part of lecture 22. Lecture 23 will be posted on YouTube at some point on Monday.